Hey, this pre-flight's on the acceleration due to gravity on any planet or moon or whatever you want to find in space. We're going to use two force of gravity equations for this one. The first one is the one you've just most recently learned, g m1 m2 over r squared. That's the force of gravity between any two objects that possess mass. We're going to relate it to mg, which is what you've been using pretty much for the entire year. This is the force of gravity on an object near the surface of the Earth. To start this, we're going to boldly say the force of gravity equals the force of gravity. Now, I have m1 and m2, but I want to be a little more specific. So I'm going to do mh, which is mass of the human, u, mp, mass of the planet. In our new function, we see mh and mp right here. And our function that we've been using for the majority of the year, we see it's mass of human, g. That's what you're familiar with. And in this case, your mass cancels out. This should be expected because this is what Galileo taught us. All objects will accelerate towards the Earth at the same rate. Your mass is independent of that. So what we get here is the acceleration due to gravity on any given planet. G, which is our 6.67 times 10 to the negative 11th. MP, mass of the planet. R, distance between you and the planet, which we can take to be the radius of the planet. And here's why. Here's you on a planet. It's really big. You are not. The equation tells us that r is the distance between you and the planet, but that does not mean we're talking about the distance between your feet and the surface. But instead, we are talking about the distance between the center of the planet and you. Now, this drawing is drawn horribly not to scale, because if it was drawn to scale, you really wouldn't show up on the surface of this planet. The planet, say for example Earth, has a radius of about 6,400 kilometers, or 6.4 million meters. You have a radius, in quotes, of about 1 meter. So your distance, center of mass, to the surface of the planet is essentially negligible. That's why we can get away with just saying, hey, you know what? Forget the person, forget the object we're talking about. Let's just focus on the radius of the planet. Now, we can only do that to some degree, because as we continue on with this unit, and we'll learn more later, it matters when you do a satellite, because a satellite has some real altitude above the planet. So say, for example, the International Space Station is about a little bit more than 400 kilometers above the surface of the Earth. So we'll have to account for the Earth's radius and the altitude at which the satellite is. So shown here in orange, it would be the altitude of the satellite, red, the radius of the planet. Therefore, green would be r, that we would use in g equals big G times mass of planet divided by r squared. So this alludes to a couple of things. One, contrary to what some people think, there actually is a lot of gravity in space. Astronauts in the International Space Station do experience the force of gravity. They appear to be floating for a different reason. They're in a constant state of free fall, but that comes later. And the second thing is that although they do experience gravity, the acceleration of gravity that they experience is not 9.81. It's actually less, because as r increases, the value of little g will decrease.